One question that I received a couple of times from grad students and even sometimes from people in the industry, which is why I need to worry about the grounded end of the outdoor insulators. Meaning that this is an outdoor insulator here. Okay, so this is the ground end here. This is my ground, and this is my high voltage. So, okay, we understand that this area will have very high electrical stress. Okay, and we have to use corona ring to reduce the electric field. But why sometimes even we found erosion in this area and the grounded end, but the voltage is zero? So how come at the region where the voltage is equal to zero, we have some erosion in the outdoor insulators? And here specifically we are talking about polymeric insulators. And that will lead us to a very fundamental question, which is when we design the electrical insulation systems, do we care about the electric field or the voltage? And to answer this question, let's go back to one of the basic fundamentals we know from high voltage engineering is that the breakdown voltage of air is what? 22 kilovolt per centimeter. And this is obviously this is not a voltage. This is an electric field. So what caused the breakdown is the strength of the electric field, not just the voltage. So what is the relation between the two? As we know it from basic electromagnetics, that if we take only one dimensional, E, the electric field is minus dV by dx. So the electric field is the one that causes the breakdown, and the electric field is basically is the gradient of the voltage, or is the slope of the voltage with respect to x. So now, having this fundamental understanding, let's go to an outdoor insulators and let's see the voltage distribution along the insulator to understand why we need to worry also about the area at the grounded end of the insulation. So here is this outdoor insulators. Assume this is the energized end and this is the grounded end. And this is a typical voltage distribution along the line. So if this is the energized end, we start from here. So we have very high voltage. And then this voltage in the small distance here drops very, very, very fast and then becomes almost constant at the middle of the insulator until it reaches the grounded end, and then we'll have here a sudden drop. So remember, the y-axis is what? Is the voltage. The x-axis is the distance. So dV by dx. Remember, dV by dx, so it's the slope. So we can see here clearly in the voltage distribution, we have two areas with high slope at the energized end as well as at the grounded end. So if we go and try to find the electric field for this distribution, we'll find this. At the energized end, we have extremely very high electric field, but also at the grounded end, we have also some increase in the electric field. And of course, in the middle here, because the slope is very, very, very small, dV by dx is almost equal to zero. And this is why we have here the electric field is almost equal to zero. So to sum up, what we need to care about when we design our insulation system is not the voltage, but how much electric field is applied to it. And this explains to us why at the grounded end we have sometimes substantial electric field, to the extent that for insulators working at voltage level 400 kV and higher, we have even a corona ring around the grounded end.